So earlier we had talked about what the intuitive definition of a derivative, I mean of a limit was. So I just want to remind you, intuitively, a limit as x goes to a, or let me write it like this. The limit as x goes to a of f of x is equal to L. This means as x gets closer and closer to a, it appears f of x is going to L. Okay, so we've looked at some examples of this many times in this class. Let me just quickly remind you, if we go to this picture right here, we looked at this picture a lot. Let's look what happens as we get close to 2 right here. Where does it look like the function is going as x approaches -2? Sorry, where does it look like this is going? Well, we gotta look at the y values, right? As we approach from the left, it looks like we're going to 3. As we approach from the right, it looks like we're going to 3. So what we're saying is the limit, as x approaches -2 of f of x is equal to 3. We don't say the function value is actually equal to 3. So notice that f of -2 is not equal to 3. So this is exactly the situation where this function is discontinuous, because the limit looks like it's going to one number, but the actual function value, in this case, it doesn't exist because it's an open circle. So this is not continuous at -2, right? What we want to do is we want to make precise this intuitive definition. And the way that we do it is kind of ridiculous. Or the definition looks like so different from what your intuition says. So this lesson is going to be very insightful for you, because it illustrates the fact that a precise mathematical definition might not be the same as what your intuition is. Okay. So my approach for trying to teach this to you is I try to break down the different pieces of the definition first, and then I'm going to piece it all together. Okay. So give me 1 second here. So the first thing I want to mention is that this is the precise definition, not the intuitive. So we looked at the intuitive definition. This is the precise one. The first thing is that we want to quantify closeness. You'll see in my intuitive definition, I say we get, as x gets closer and closer to a, f of x is going to L. So maybe instead of saying going to L, I could even switch that to f of x is getting closer and closer to L. So we need to quantify this idea of closeness. That's our first objective. Okay. So if you look at this guy right here, this is f of x minus L. The f of x is the f of x, the function that we're looking at, the L is actually the limit that we're talking about. What does this inequality mean? Well, way back in the 2.1 homework, or I can't remember which section it was in, but I had that question where you kind of go at a certain distance on either side, and that's like within a certain distance. So we can think of absolute value as distance, and this guy is basically saying that the distance between f of x and L is less than epsilon.
Professor, are you writing something? Because I can't see it.
All right, let me reshare my screen. Sorry. Sorry, hold on a sec. Something screwed. Okay. How long have you not been able to see anything this whole time? Because I just saw Brittany's comment.
I saw you write the red part.
Okay. I accidentally clapped myself. I didn't want to do that. Oh well. Oh, there we go. Undo that. All right. Wait, I'm still clapping. No clapping. Is there a stop clapping option? I give up. Back to this situation at hand. So remember, absolute value can be interpreted as the distance between f of x and L is less than epsilon. Okay. This is the equivalent to this statement that if I have my f of x, I can bound it between two numbers. And the first number is L minus epsilon, and the second number is L plus epsilon. Okay. The next idea of quantifying close, these are closeness of y values. So this is like y values even here. The second part we want to quantify closeness of is x values. So if you come over here, these guys are x values. Okay. So how do we interpret that? Well, this is really the same thing. We just, instead of working on the y value part, we work on the x value part. So this is the distance between x and A is less than delta. And that's equivalent to the states basically saying that x is going to be between A minus delta and A plus delta. Okay. Now I want to refer to that, that link that I sent in the chat box. If anyone didn't see that, you can I can repost it, but let me show you over here. Let me share my screen. So in this case, do you see how they call this? The function is going to be f of x squared. F of x is equal to x squared. So that's this curve right here. And they're not calling it A, they're calling it x star. So this is playing the role of A for us. If I change this to A, I hope I'm not ruining things for people. I hope I'm not messing things up because I just wanted to match your notes. So Did I mess it up already, actually? What happened to the bar below here? Let's undo. Wait, let me just refresh this page. Okay, I need those red bars. Sorry, I want to change it to A to make it clear. In your head, you can pretend that this is A here. Okay. And then so if you look at this case, my A is right here. My A is 2. And we're trying to say, oh, the limit value is 4. If you think about it, that makes sense because 2 squared is equal to 4, right? So what I'm trying to show you here is, oh, I can change this epsilon. If epsilon is really big, it's like this. If epsilon is really small, it's like this. I can also change the delta. So the delta is the X thing down here. So if delta is really big, it's like that. If delta is really small, it's like this. So the way that I haven't told you the definition of a limit yet, but I want you to notice that if I have a big delta here, I get a red bar. But when I move it closer and closer, if I get within a certain distance, it becomes green. Oops. I have fat fingers, fat imprecise fingers. Let me make my purple a little bit bigger so then I can make my green a little bit. Like that. Okay, so you'll see, you'll notice that once it's green, then that guy has a little smiley face there, right? So the basic idea is that if you took any X values on this green part over here, then when you map them up, you would stay inside this purple band. Okay. So I haven't told you the definition yet, but I'm in the process of explaining. So let's go back to our worksheet. Okay. So we understand you have an epsilon band on the y-axis, that's the purple thing. And then you had the delta band at the bottom, and that was the red or green thing. So let me tell you what the official definition of the epsilon delta definition of a limit. It basically says for every epsilon greater than 0, there exists a delta greater than 0 such that whenever, or let's say if f of x minus L is less than epsilon, then x minus, sorry, I have it backwards. Oh, sorry, I gotta ruin your notes. If x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. This is the official definition. So this definition has many pieces. So let's unpack the pieces first, and then I'll explain how it works. Okay. There's something called a universal quantifier. So the universal quantifier is this for every epsilon greater than 0. They call it universal because we have this statement like for every. So it sort of applies to any number epsilon that's greater than 0. Okay. An existential quantifier, sorry, an existential quantifier is basically saying something exists. So right here, when we say there exists a delta greater than 0, okay. And then the conditional the conditional statement is basically saying an if-then type statement, right? So, you say it says such that, so this is saying a condition is on the way, and then the actual condition is this part right here. Okay. So the universal quantifier part is really the for every. The existential quantifier is there exists. And then the conditional statement is sort of the if-then statement. Okay. So we could break this down. For every epsilon greater than 0, what does that really mean? That means for every positive, because it's greater than 0, for every positive epsilon. And remember, for every positive, I guess we should say distance epsilon from L, there is a number delta. There is a positive number delta. Actually, it's not just a number, it's a distance. So I'm sorry. Let me make that a distance, a positive distance delta from A, such that means, I don't know, such that. I don't know how else to translate that. This part is the really mathy part, and this is the conditional. So this guy says, if X is within a distance delta of A and X is not equal to A, then f of X is within distance epsilon of L. Okay.
Professor.
So, oh, let me switch captions here. Hold on.
Thank you.
Oh, you're really quiet. I don't know what happened. My volume up? I barely heard you. Kate, right? Kate, yes. Are we good, Kate? All right. All right. So the way that you can think about this is, you can think about this as like a game. This is like a game. Okay. Someone gives you epsilon, and you supply the delta so that the conditional is true. Okay. So I wanted to show you with that little Desmos thing. So you can play with it yourself as well, but I'm going to share a different screen here. All right. So let's say, like I said, this is a game. Okay, so our A is 2, our L is 4, just like before. Let's say that someone says, you know what, epsilon is equal to 3. Okay, so they give us this wide purple band here. So this is going to go up to 7 or three like this. So this goes up to 7. In other words, 4 plus 3. And then this band goes down to 1, 4 minus 3 like this. And then once someone else has given us the epsilon, we get to choose delta. So if my delta was way out here, it doesn't work. But as I move delta closer and closer, at some point, we stay inside the box. So here we're not inside the box, but maybe if I change it to like 0.6, now we are inside the box, right? So what happened? They gave us an epsilon equal to 3. I could find a delta so that all my x values map to within epsilon of the y values. But I have to always be able to win the game. So let's say, someone else said, oh, I didn't mean epsilon was 3. I meant epsilon was 2.5. Now, do you see how my purple band got narrower? So I have to be able to narrow my delta band. So if I move this guy smaller to 0.5, oh, now we're still okay. So let's say I change this to 2. Oh, my old delta didn't work, but I can make my delta smaller. And then now it works. I could make my epsilon equal to 0.5. Then I'd have to change my delta. Maybe my delta needs to be 0.2. Is that going to work? 0.2 still doesn't work. Is 0.1 going to work? 0.1 works. And as long as I can keep playing this game, as long as I can keep winning this game, no matter what epsilon they give me, the limit is going to exist. So let me try to choose something more ridiculous. Let's say I did 0.1. Can you see that? Okay, 0.1 didn't works there. So then where should I change this to? Maybe 0.1, 0.5? Does 0.5 work? No. Does 0.3 work? No. Does 0.2 work? Yes. So when they give me an epsilon, no matter what epsilon they give me, I can always find a delta that works. So a lot of times when people talk about epsilon delta proofs, they do this to represent the epsilon band, and they do this to represent the delta band. So the idea is for every epsilon they give me, if they shrink epsilon here, I can shrink delta here so that when I map it up, I stay within the epsilon band. That's really the precise definition of a limit. Okay. So let me share my iPad again. Okay. So I want to show you something real quick. So let's just draw a picture of a situation where the limit doesn't exist. Maybe I could copy a picture from earlier. Let's copy this picture right here. So let's say suppose someone says the limit as x approaches 1 of f of x is equal to 6. Okay. First of all, do you guys see why the limit's not equal to 6? Can you explain to me real quickly why the limit's not equal to 6?
Is it jump discontinuity or?
It's a jump discontinuity. If you come from the left, it's equal to 6, right? The one-sided limits are different. The left side and right-sided limits don't exist. I mean, are not the same. They're not equal to each other. These are all correct. All 3 of your answers are correct. So I want you to pretend now that, oh, okay, well, we're saying this part right here is L. This part right here is A. If someone gives me an epsilon band that looks like this, let's say we go from 7 to 5. Can you guys see that on this right-hand side right here, this part of the function is always going to be outside of that purple band? Can you see that? Can you see that? This part, the left part, is inside the purple band if I can make it small enough. But the right side has no hope. The right side is going to be, the right side can't be up in the purple band because we have this jump discontinuity. So I'm just trying to give you an example of a situation where the limit doesn't exist and it fails that precise definition of a limit. Okay. So so does anyone have any questions they want to ask me about this first before we actually try to do a problem? I find that once I show this little epsilon band and delta band, students understand that part, but maybe they don't understand how to prove that the limit is something. So I want to show you that next.